This is the University of Alabama in Huntsville. I am a part of one of 3 senior design courses that will be building an aircraft throughout the whole academic year. We're almost wrapping that up with our test flights coming up for those aircrafts in the next week on Tuesday. So for an overview real quick, I'm going to talk about the project. We have missions and requirements behind the project, along with our aircraft design, the aerodynamics behind it, the propulsion, all the good stuff that makes up a good plane. Let's talk about our team here. We got Devin Brown over there. That's our team lead and chief engineer. He has helped fabricate the plane and made it for what it is. We have Rayota, who did the stability and control with a program called X-Flyer 5. This was developed by an MIT professor. We have Sarah Stearman. She is just awesome. She helps with reports. She's everywhere we need her to be. Jacob Bussey, Cameron Lay, and Alex Steele. On the bottom, those were helping with other portions like our landing gear, our payload, and our structure. For the overall project review here, we have to analyze and develop a plane to fly at the end of one academic year. The requirements behind this are fairly simple. Have your wingspan under 10 foot, have a payload of minimum 2 pounds of water, and a maximum takeoff weight of 12 pounds. We will be practicing engineering techniques for preliminary, conceptual, and detailed design reviews that we went through and had hour-long discussions with our professor and telling them how we are going to build this plane. And our most important, in my opinion, is the overall teamwork on the team and making sure everyone is getting their role done and no one is interfering with their components with someone else's. For our 3 missions, we will be flying our mission 1 with 0 water, our mission 2 with 2 pounds of water, and our mission 3 with our maximum water available to carry. The mission 1 and 2 will be done with 2-mile laps around this course right here. This is 5 laps, as you can see on the top. And then our mission 3 is maximum flight distance until you have a battery life of 20%, and then you'll take it down. For the overall aircraft design, we went through a figures of merit, and this was done with weighting what we thought was most important with different things like our efficiency, effectiveness, weight, simplicity, fabrication. And the one that was selected from this all was the flying wing. We went with that. So we decided to start with some initial stages. We saw some winglet changes. My personal favorite, the spoiler on the back, I thought that was pretty cool. Teammates didn't like it, so we selected the features of the plane that we liked and desired. 2 of those came out. We had a duct fan concept going and a blended body. From this, we took what we liked from both designs. We liked the fuselage shape, and we liked the blended body more for flying purposes and stability purposes, along with the duct fan cost way too much power to maintain flight. And you can see at the bottom, that is our final plane. I'll have another picture in a second. Our wingspan is 7 feet wide, along with a 30-degree sweep right there, and other sizing you can see. And that is a picture of the, and this was all done with a program in CAD developed by Autodesk, Fusion 360 for anyone who knows. Then we have our internal structure, and this is our components inside. We have our battery at the top with our motor at the bottom, and this was the most important of all weight components because these are the heavier weight components. Our battery is most forward while the motor is most aft. This allows us to have our CG at the location we want, and there was actually a neat feature. The battery weighed double of the motor, so we were able to put the motor double the length of the battery away from the CG location. Then we have right here our 4 tanks. These are our 4 water payload tanks that we will be using with 2 servos on the side that will be controlling our elevons. These are our elevators and our ailerons. We will have pitch and roll control, but we will not have as easy with yaw. But with that, flying wings are able to have yaw control with roll, and pitch alone. Design configuration, we have for mission 1 and 2. Mission 1, simple, no water. Mission 2, we're going to fill our 2 and 3 tanks up, and this will keep our CG at the same location. And then for mission 3, we'll be filling up all those tanks. For the aerodynamics of it, we had to look at our airfoils. Airfoils are very important when it comes to having a wing, but with our case, we don't have a tail. So we need to find an airfoil that had a low moment coefficient. This means we won't tip either way as easily. And with that, we looked around and found a series called the MH series. It was developed by Merton Hepperly. We looked at the MH60s and the MH40. The MH40 had more theoretical behind it, while the MH60 had more empirical data behind it, so we went with the 60 series. And from that, the MH64 was chosen due to its thickness out of the bunch was lower than the others. Then we have our power required curve. This was developed with having now an airfoil shape with our body known. Then we can solve for our aerodynamic properties and solve for our drag. With not needing our power required, this will be how much energy the plane needs to actually stay afloat and fly. And with that, we looked at the drag times velocity, and this is being able to solve for power required, because if you look at your thrust required times your velocity for trim flight, it is equal to each other. With this, we have our max endurance. This is found at the lowest point of this power required curve. And might I add, you see this power required curve is messed up, surprisingly. Right here is supposed to be 35 feet per second. When we were using the XR5 program, it could not solve for our power required, our drag, and other components for that, because it could not actually solve them below the stall speed, which was 35 feet per second. So right here, it's not meant to be 0, it's actually 35 feet. We also have our max range speed, and this is drawn from a line from the origin tangent to our power required curve. And right here, we found that at 60 feet per second, so we'll be flying at 60 feet per second. For our motor, propeller, and battery combination, this was a very tricky topic to deal with, because we are not electrical engineers, as the last group said. We are aerospace engineers, and going through this, we had to ask around, get opinions. We also used the UAS lab on campus to get good ideas of what we should be looking for. So we chose with this our battery as 6,000 milliamp 6L, our motor as a 450 kV, and our propeller, we actually have two choices. We have a 13 by 10 and a 12 by 8. The 13 by 10 is going to be the one we're going to mainly use in flight. We're hoping we could get the 12 by 8 because the pitch is lower, and this will cost less energy to power. The propeller is also a folding propeller, and as you see, this is important because I didn't mention earlier, a flying wing, if anyone's ever seen, normally doesn't have landing gear. We will be having our landing gear actually after flight fall off to the ground, and when we come in for landing, we will be doing a belly land. Folding propellers are useful for that because you don't want to damage your propeller. We also used a website called eCal, and this was, for anyone knows, you're able to put in your weight, the components that you're wanting to fly with, and being able to see what that combination will do. And we went through several iterations until we found the one we liked, and we found the thrust was maxed at 11 pounds. The power available is at 655, and you'll see why that's important in a second. And then our estimated time of flight, which is 8 minutes. With our propeller, our motor, and our battery, we're able to take such things to the UAS lab on campus. This is a useful tool to have on our campus, and I just do want to say I also work there. It's pretty neat, and my mentor down here, Chris Salas, helped out with getting us thrust stand thrust stand data to compare with our ECAL results to make sure the combination is doing what it said it should do. Right here, we tested 4 different ones actually. For ECAL, you can see in blue the APC, which is another type of propeller series, and they actually have their own database behind what their propeller should be doing. We wanted to compare that with our Aeronaut, which is the propeller we'll be using, and we also had a APC propeller, which you see lined up perfectly. They are the same exact propeller right here, the yellow and the gray, so our thrust is exactly what it should be. For our rate of climb, we're able to get from our power available minus the power required over the weight, and this is important because you can see things like your rate of climb from this. Rate of climb is able to determine how fast your plane can actually lift, and for flying wings, they often have very high rate of climb. And on a side note with all that, at the Rotorcraft Center, I also worked on flying wing in the fall semester, and this is actually what influenced my own personal desire to build a flying wing. With that review, we can actually see where our power available lies with that power required curve all the way up there to far up. That distance right here also is when it's at its most minimum to the power available up at the top is that rate of climb. For our stability analysis, we use the program called XFlyer5 mentioned earlier. We were able to design the actual model of the plane in XFlyer, which was awesome. None of us actually first knew how to use it. And then our teammate Ryota, he just went at it and learned everything he needed, and he actually shared that information with the professor, and it's been very interesting. We chose our CG location at 1 foot, our neutral point at 1.5, and our 1.44, and our aerodynamic chord at 1.49. From this is important so we can solve our stability margin. That is the neutral point minus the CG over the mean aerodynamic chord, and we solved at 30%. Our own requirement and self-made requirement was 25% because we have a flying wing. They're often very scary to fly for the narco pilots that will be flying our planes in just a couple days, and so they asked, let's make sure we have that number pretty high so our plane won't be moving around crazy and doing flips that we don't want it to do. For our longitudinal stability, we needed our CM versus alpha. This is our coefficient of moment versus the angle of attack with our stability margin, also mentioned 30%. With longitudinal stability, in order to determine, and this is for pitch, so for your plane going up and down, how do you know if it's stable? Well, you need basically just 2 things to really help out, which is the slope negative? Yes. Is our CM naught, this is our coefficient of moment at 0 lift, greater than 0? Yes, it is trimmable. We actually have that trim angle right here at 0.6 degrees. With XFlyer, we're also able to solve what our deflection angle for our elevons needed to maintain that angle of attack, which was 3 degrees upward deflection. And for our lateral and directional stability, we used an open loop dynamic response. This was to use a side gust wind on the plane at its 10% and 20% free flight velocity to see if our plane would actually come back to equilibrium. And from this, we see a change in flight. This is after the disturbance is made. Then we have our roll rate, our yaw, and our heading, and you see a little diagram right here showing what all those are. And this is just showing how the plane corrects itself into position. And at 3 seconds, we have our plane actually coming back to equilibrium. We think that will be fine. For our stability, we're unsure. We'll actually find out during our test flight on Tuesday. For avionics, this is what makes up the innards of your plane, from our motor, battery, and ESC combination. And ESC also is what controls the battery or magnets inside the motor and allowing it to turn. Our Pixhawk is our flight controller, and this will be telling the motor how fast it should be spinning. It will also be telling our servos what they should be deflecting, and then our receiver will be going inside of it. The GPS will give it its coordinates, and the telemetry radio on board will be sending its data back to the ground in real time. On another diagram to see that with this data that's going behind it, we have our transmitter. This is with the pilot. It goes to the onboard receiver. That onboard receiver goes to the PICSOC. While that's happening, the GPS is powered and receiving its coordinates to go into the PICSOC, to the telemetry radio, to a program called Mission Planner that will tell us all our things such as our change of velocity, our altitude change, rate of climb, just various things that we would actually care to know about our plane when we're flying. And then we can also have that data go to a computer for processing later on. The Mission Planner is a hooks with your flight controller, that is the PICSOC, and it's a simple interface as you see. It looks really neat. That actually moves with the plane right here, and we can also track its coordinates from above. It's a very neat program for anyone who has not actually seen it before. For fabrication, now this was honestly the trickiest part, I think, of our project, because building a plane such as ours, we used a material called carbon fiber with resin to develop a composite plane, and we had to do this using negative molds and a wet layup process known as bag molding. So we started with our first having a CNC print out the airfoil shapes for the fuselage, the wing root, and wing tip, and then using the space in between, we filled with foam and a hot wire cutter, which has it's like a nickel carbon wire with electricity ran through it, and it was able to cut through the foam and matching that airfoil shape. Then the last was our wet layup, which is putting a bag followed by your composites, your resin, and then perforated film with a bleeder cloth and bleeding cloth and bag over it all to then be sealed with tape and a vacuum seal. Here's some pictures of us in development of that plane. We started with the bottom here, and these are the negative molds for that. You see little markings and rough edges. This was sanded down and then painted over and filled in so we would have a more smooth skin when it is bagged. Here's a look at what that bag is right here, and this is actually the foam colored in with that paint that I mentioned earlier. It was heavy, it covers it all. It's actually supporting the foam itself so it doesn't get destroyed. So we now have the ability to make more of these. Here's a look of that plane right here at the bottom. We made the bottom from one piece and the top from 3 pieces. That is the wing, fuselage, and other wing. Right there, bam. And then we have our elevons cut out. The X-Fire 5 program was also able to help us determine what our sizing for those elevons were. And there's another look at the final aircraft and how beautiful. Just take a moment. It's not fully assembled. It will be this as of right today and this weekend while I'm gone. The team is working hard and diligently to pass our airworthiness certificate. That will be done on Monday with checking our plane and making sure it's safe to go up in the air. And then following that on Tuesday, we will be putting it in the air with the other 2 teams that are also in the course. For an overall summary, this project has been an absolute gift and a learning lesson too of how it feels to work with a team, how it's able to see what real aerodynamic systems look like, along with trying out new things like fabrication, electronics, things that a normal aerodynamic engineer like myself don't get our opportunities around. Any questions or comments with that?
With the addition of the water weights, how are you accounting for any sloshing effects that we're going to see on that?
The payload tanks will be filled to maximum, so there won't be any sloshing. They'll be filled completely. That's why we have those 4.
So each one is a pound of water. So if you can only take in 3 of them, then that's going to mess up your center of mass.
That's right. So if we were to go down and if things were to weigh too much, we would just go down to 2 tanks instead of going down to 3, because like you said, an odd number isn't good, evens are better.
Let's see, the, two questions for you. The first one is, when you think about these very low subsonic designs, you think you'd just do a straight wing exactly 10 feet to get the maximum area and then optimize the leftover drag. So what drove you to a swept wing, tapered wing in this specific design?
The sweep was needed to actually improve your stability margin.
Okay.
Yep.
That's it. And then I don't see any vertical surfaces to be able to, you know.
We do have winglets. They are not put on. You've seen one right here and the other one over there.
Can you talk a little bit? I didn't see in your traces any discussion about that troll mode. So can you talk about frequency damping of that dynamic mode and what you think you'll see with this?
I've actually used the flight simulator at my work. It's a handy tool to use, and they have actually a flying wing in there. I do not know the exactness of the frequencies or anything that you input, but I do know the flight maneuvering behind what we will be expecting for our turn. The flying wing that I'm referring to in the flight simulator also has only elevons to it, so I picture it be very similar, and when taking that knowledge and bringing it to our plane.
Thanks.
Anyone else? Yes, sir.
More of a comment, that your 30% static margin seems excessive.
It does. The narco pilots wanted us and at first it was only at 15%, and that was because the sweep wasn't as large then. They asked during the system concept review to increase that, and we did. And 30% was now our new one, and yet we're still receiving, oh, now it's too big, now it's too small. It's a hard thing to judge what your stability margin should be, but we think at 30% is well beyond fine. It is large, yes, but it should be fine nonetheless.
With the flying wing too, you know, you have the static stability because you swept the wing, you have the positive static margin. You should also look at the dynamic stability of it. So that's where the flying wings, especially the small scale, like to run away.
But, oh, yes,
Your
yes.
food void gets bigger.
Hmm?
Your longitudinal mode grows. It's statically stable, but then
Also with that stability margin, the being greater also means the plane is more nose heavy, which is fine for us. Having more nose heavy plane, it just means higher deflection, and that's fine. We can take the drag because our plane is the most efficient when it comes to drag. So a comparison to the other two teams who are doing more traditional designs. So we feel the need that would be fine to have more deflection if required.
Any more questions? Thank you.
Yes, sir.
I don't think I caught it. What was your methodology for testing for crosswinds?
Crosswinds? We're using the XFire program, and it's able to see an open loop dynamic response from this. We're able to put side gust winds in one axis on the side, so it's actually hitting the plane from the side in the program, and it's doing this at two different velocities with them colored green and blue for you to see. Does that help? I actually am not an expert at the X-Firefly program. My teammate Ryota, he's been well off with it, and I wish he was here to help better your question.